So this is an overview of this is the overview of what we're going to do here. We're going to look at basic algebra. The first thing that we'll do is we'll do three things. We'll look at systems of linear equations, then we'll look at determinants, their inverses, and then also in addition we'll look at matrix algebra. So basically those four things make up our basic algebra. So let's start with the first thing, which is systems of linear equations. Systems of linear equations are what we used to call simultaneous equations. If there were two equations and two unknowns, x and y, then you had two equations. Then maybe at A level you did some equations where you were solving three equations and three unknowns, x, y, z, and then three equations, and then you solve them. So the way to solve this equation, there are basically three ways. For simultaneous equations, which are only two-dimensional, you can plot them on a plane. You can plot those ones on a plane, and the solution is given by the point of intersection. So you can extend it even to 3 dimensions. With 3 dimensions, now your linear equations will define a plane. So it will determine where your planes meet. So you can imagine in a 3-dimensional space like a room. Then one wall and the floor can meet along a set of a whole line at the floor, several points. Then the floor and the two walls can meet at one point at a corner. Then if sometimes the floor and the back wall don't all meet, 3 of them don't all meet. So what will happen is that what will come out of that is that your solution sometimes depends on whether you're going to have many solutions, an infinite number of them, or you're going to have just one solution, like the one point at the corner of the room where your floor wall and two walls in the floor meet. And then sometimes you don't have a solution. The back wall and the front wall don't necessarily meet. So that's one way of solving, graphical and plotting them. But our plotting is limited up to 3 dimensions, on a 3D. The more dimensions, then it becomes a hyperspace. You will not be able to plot them. Then the second method was you would eliminate one unknown at a time. You eliminate x or y, and then get the other one. If you get the other one, then you solve the equations knowing the solution. So the method that we are going to use here is basically an elimination method, which is called Gaussian elimination. The third method is to get an inverse. Get an inverse of the matrix which represents your system of equations. And you can just multiply both sides by the inverse. That will give you your solution. So getting an inverse of a matrix is not an easy matter. It is a subject matter of what we are going to do in the third part. We are going to obtain inverses of equations. If you can obtain an inverse, then you can solve by just multiplying by that inverse. So let us just get into an example, typical example. We'll solve this equation. This equation is an equation. There are 4 equations and 4 unknowns. The unknowns are x1, x2, x3, x4. So there are 4 of them. So what you will do if you want to solve this using our Gaussian elimination, we'll do this. We will represent this as a matrix. So you get a matrix A, which we are going to call A, which is just the coefficient of these elements here. So you take the coefficient of x1 as the first column, x2 second, and so forth. Then the right hand side is the right hand side, what you call your bin. So if you do this for this system, we have what we are calling the augmented matrix, which is this augmented matrix. On this side here, on the left hand side, you have the coefficients of the unknowns. On the right hand side, on the right hand side is just the numbers that you have there. So this is your line of partition. It's indicating that this is the left hand and the right. So for our initial row operations, what we are going to do is to eliminate. We are going to eliminate x1 in the last three equations. Okay? So we may keep it in the first equation. So we use this one as what we call a pivot. So if you multiply this equation number 1 by 2, and then subtract it from row 2, and set that to be row 2, so you will get a 0 here. So this is what these row operations are doing. So because this one is matching with this one, you can, if you subtract row 3, if you subtract row 1 from row 3, you get a 0 here. And the third one is that if you multiply row 1 by 3 and then subtract it in row 3, you get a 0. Or in row 4, sorry, you get a 0. So these operations will introduce zeros here. They will eliminate x. They will eliminate x in the eventual all equations. So here what we did is we performed these row operations. Row 1 is remaining as this, but the new row 2 is obtained by doing this operation. The new row 3 is obtained by doing this row operation. And the new row 4 is obtained by doing this. So how do you perform this operation? You take, for the first one, you take whatever you have in row 2 and subtract 2 times the corresponding element in row 1. So to get this element, this element here, you are taking minus 1, then subtract 2 times 1. So you end up with minus 3. So we did this for the rest of all these elements. And for these ones, we just subtracting what you have at row 3, you subtract what you have at row 1 in the corresponding elements. Then you have this, we did it for the 3 elements and we ended up with this. And the last one, same thing, following this. So after doing that set of 3 initial row operations, you have this system here. So now go to the second stage. If you just look at what we have here now, if you now just look at what we have here, we have a 1. I think I want to go up. Yeah. We have a minus 3 here. So what we are going to do is to make this minus 3 1. Or alternatively, you can swap this one and that one. Then you change the sign of the things here. So that is also possible. You can do your row operations in any order, and according to whatever test, whatever you feel like doing. So in this case where let me go down. In this case now, we are taking that row, for row 3, we are going to divide it by half. Then we are going to swap row 2 and row 3. So this will give us this. So row 3 has been multiplied by half. Then we swap row 2 and row 3. So it will give us this new set of row operations. This new result. 2 and 3 has been swapped. Now, if you have that, you can do another set of row operations. The target is to eliminate this one. You eliminate this minus 3 and this minus 1. This is done by doing these 2 row operations. So if you take row 3 and multiply 3 times what you have at row 2, that will eliminate this element. And if we add row 3 and row 4, it will eliminate this. So you do these row operations. This new set of row operations will give you these new coefficients. Now what is happening is that the number of zeros is increasing, is going to the right. We've stepped to the right. So next, you look at this, the last 2 by 2 matrix here on the left hand side. You can go and do this again. You can make this minus 4 a 1 by dividing by 1 over 4, and then you use it to eliminate this 2. So if that is done, you have, these are the row operations that we are going to do, here. You are going to take this row 3 and divide it by minus row 3. Then now you have a 1 here. Then you are going to add 2 times that. So if you perform these 2 row operations, your zeros are increasing, going to in a progression to the right. So now you have the last equation is this one. So your matrix is now in what we call row echelon form. Echelon is a Greek word for step. So they are stepping all the way to the right. Now if you have this last equation, what it means is that you now have minus 12 x4 is equals to minus 6. So it means you can use the last one to solve for x4. So you use a technique which is called back substitution, which we are going to do here. So row 4, the corresponding equation is this, which means that x4 is equals to half. So if we use half, row 3, if you just go up, row 3 is just saying x3 is equals to 2. So that one is given. Row 3 is equals to 2. Where were we? I think I lost it somewhere. Yeah. Row 3, I wanted to go just one up. So row 3 is just equals to 2. Row 2, if you multiply out, remembering that the corresponding columns are the columns corresponding to the respective unknowns, you get this equation, which will give us, because we can substitute for x2 here, and it will give us that x2 is equals to 1. The last one, which is just the equation that we had, which we did not change. We now know x2, x3, and x4. And then we substituting into that, then that will give you x1. So our solution is the solution is the 4 unknowns, x1, x2, x3 to x4. So this is your solution. So in this case, we're able to get a solution of the equation, which is just one unique solution. A unique solution, just one single point. All those 4 planes meet, all those 4 planes in the 4-dimensional place, they'll meet at just one point. So our solution is just minus 1, 1, 2 and a half. So let us go now to look at a solution that is inconsistent. So what do we mean by a consistent system? A consistent system is like the system that we've previously solved, which we have just solved. It's a solution where you can actually obtain a solution. It's a system where you can obtain a solution. You can obtain values for your unknowns. An inconsistent system is one where you cannot solve the system. So we have this system here. 4 equations, 4 unknowns. Let us do what we did earlier. We write the initial augmented matrix, which is the matrix representation of that system of equations. On the left hand side here are the coefficients of the unknowns, and here you have the right-hand side. Let us look at the row operations that we do. We use this as the pivot and eliminate it. Multiply this by 2, row 1 by 2, subtract from there, you get 0. Multiply this one, row 1 by minus 3, subtract it from the 1, you get 0. So these 3 will be zeros. Row 3, just take it and subtract 3 times row 1. So we have those row operations. We are just trying to eliminate x1 from row 2, 3, and 4. These are the row operations. And you perform them. If you perform them, they will give us this set of. So what I implore you to do is to actually try to carry out these row operations and verify that you actually get this. That's important. Now here we have this 4, which is lying there. To get it, to do it better, so for us to be able to do this better, you just need to swap row 2 and row 3. So if you swap, they become this. Now we have a system of equations. These last two, you can actually eliminate x3 in the last equation by making this first, the x3, this minus 3 a 1. So you divide by minus 1/3. Then you multiply it by 3 and subtract and add it to the last equation. That will make you eliminate this. So you pick this to be a pivot and use it to eliminate that. That's the next step of row operation that we do. So we can eliminate x3 from equation number 4. Remember, your rows are just as good as equations. So if you perform that, then you are going to have a row of zeros. This will remain as it is. We've just left the leading elements not as 1 necessarily, because it was just easy to do this. So what does the last equation tell us? This is what we will get. Row 4 tells us it's 4 times x1. There's a 0 multiplying x1, 0, 0, 0. All the things on the left hand side are zeros. You're multiplying all zeros, and then you are saying this is equals to 1. And because you obtain 0 here, it means you are saying 0 is equals to 1. But this is not true. 0 is not 1. So we have a contradiction here. So it means that this system, it is inconsistent. This cannot happen. So this system is inconsistent, and we conclude that it has no solution. So those equations, these 4 equations in our second example, which we have reduced to this, it means those equations do not meet at any point. They are like 2 parallel walls in a room. 2 parallel walls, 2 opposing walls, they will not meet. They will not meet, but 2 walls which are like the front and the side, they meet. They meet at a vertical point. They will have solutions. So that is the second case of systems of equations. The second case where you can fail to have it can have no solution. Now let us go to the third example. The third example, we want to solve this system of equations. 4 equations again, 4 equations, 4 unknowns. Let's just do what we've been doing, take it to argumented form, and then perform some row operations. So now I think you are familiar with what we are doing. I've maintained a situation where the first element is always the one that you use. So we do these row operations, and if you perform these row operations, we eliminate x1, and your system becomes this. So the system becomes this. What I'm telling you is what I want you to observe is this. These equations, the 3 remain, they have the same coefficients except for different signs. So what it basically means is that these equations, contain almost the same information. So let us do row operations further. We do 2 more row operations to eliminate things here. If we eliminate that, because they are corresponding and the same, what will remain is just the second equation will remain as it is. But the other ones, the coefficients just cancel out right up to the right hand side. So all terms on the left hand side, on the right hand side, for the last 2 equations become zeros. So we have rows of 2 zeros there. The rows of 2 zeros. So let us analyze that solution. So it means that if you have a row of zeros, it means that system of equations, there are 2 free variables, which means the system has an infinite number of solutions. The system has an infinite number of solutions. 2 free variables, you can set them to be whatever you want. So you can make x3 to be equals to s and x4 equals to t. So that is the solution of the last 2 equations. We go to the second equation. The second equation is this one. It means you can obtain x2 in terms of x3. But x3 we have set it to be s. So it means x2 is equals to 5 minus s over 3. So that gives you x2. We go to the first equation. It is this equation. Here we know x3 and x4, they are arbitrary when we have fixed them here, our 2 variables. So these last 2, we have them. And x3 is given by this. So we can get x1 from those 3. And it will get this and that. So this is equals to minus 4 over 3 minus 2 over 3 x minus 2t. So that is your solution. So what is our solution of equations? We get our x1, x2, and x3. So if we rewrite this, our x1 is equals to 4 over 3, and then there's a part in x, which is that one, and a part in t, which is that one. So we've obtained our solutions in terms of a constant term, then a coefficient of x, and a coefficient of t. So this solution is called a parametric solution because s and t are just parameters. We can choose them to be anything. So you can set x to be 1, x to be a third, and so forth. And for whatever value that you set, you get a solution. So in this case, you are going to get an infinite number of solutions. So your second system of this third system of equations is an infinite number of solutions. Now, so we have those 3 those 3 situations: no solutions, unique solutions, and infinite number of solutions. So sometimes you might want to see, without actually solving your system, you might want to see what is the nature of solutions that you have. So that is the next part of what we are going to do. We are going to do this system of equation. Just for simplicity, we're now going to solve a system of 3 equations and 3 unknowns. But here there is a variable in our equations. K is a variable. We are going to change our K. We are going to change our K, and we are going to make it. We are going to change our K, and then we are going to make. We are going to look for values of K, for which the system will have one of those 3 cases. Either it will have no solution, or it will have a unique solution, or it will have an infinite number of solutions. So we want to look at this this scenario and see what would happen in that case. How are we going to do this? We are going to do it in precisely the same way we have been doing. You get your equation, express it as an augmented matrix, express it in the matrix form, then perform some row operations. So that is what we do here. Our augmented matrix is this. Then you perform row operations. We want to eliminate this 2. So we just take row 2 and add it to 2 plus row 1. You want to eliminate this 3. Just take row 3 and subtract 3 times row 1. If you do that, you have this. These are the solutions that we have. 1, 1 plus 2, and k plus 4. Then for the second one, we have this, that, and that. So next, we are going to do the same thing. We have this. We are going to eliminate this. So to eliminate this, what you do is you take row 3, multiply by this times row 3. So it will eliminate this row, what you have at row 3. So that is the row operation that we want to do at row 3. You take row 3 and multiply k minus 6 times row 2. Then if you do that, you are going to have a zeros here and a 0 there. If you just carry out the operations, you are going to have this being equals to that. Now what we have is this. The third equation, it means this multiplying by z is going to be equals to that. So this is going to determine the nature of our solution. If the left hand side is 0 and the right hand side is not 0, then you have no solution. If the left hand side is not equals to 0 and the right hand is not equal to 0, you have a unique solution. But if they are both equal to 0, then we have, if the left hand side and the right hand side are both equal to 0, then we have an infinite number of solutions. Remember, if you have a row of zeros, then you have a unique solution. You have a unique solution. So let us go down and see what this does. So to analyze this, you just need to look at how that element does. If the left hand side is equals to 0, it means this. You get this equation. It's a quadratic which has these two solutions. So it's at 2 plus or minus root of 3. So the right hand side value for the right hand side, if you have the right hand side being equals to this, it means if k is equals to this, you substitute on the right hand side, you are going to have minus 2k plus 9, which is not equals to 0. This is not going to be equals to 0. So this tells us two things. There will be no solution if you have k being equals to either of this, which means the left hand side is 0, the right hand side is not equal to 0. So we are not going to have no solution if k is equals to 2 plus root of 3 or k is equals to 2 minus root of 3. Then you have a unique solution if the left hand side is not equals to 0. So if this is not equals to 0, the right hand side we have a different solution. So as long as they are not what we have obtained here, you are going to have, as long as they are not these 2 plus or minus root of 3, you are going to have a unique solution. Then, are we going to have both the left hand side and the right hand side being equals to 0? The left hand side and the right hand side not being equal to 0? No. So there are no values of k. So this system will never have an infinite number of solutions. So the solution set is the empty set. So there we are, and this is what we have on systems of equations, systems of linear equations. So let us stop there for